In this next lesson, we're going to look at photoelectric effect. So this is an experiment that looks at supporting the particle theory of light. When light is shone on a metal surface, so this would be the photoelectric surface, electrons are emitted. They travel across the vacuum in a tube to a metal conductor, which detects a current. So here's the light rays coming in from a light that's shone, hitting this photoelectric surface. The electrons are being emitted this way. They travel through the wire. That's going to be a multimeter that's going to detect current. So current, we know, is measured in amps. When you shine the light on that photoelectric surface, either the electrons are going to move or they're not going to move. It's not going to take time for the electrons to build up energy and be ejected. They're either going to go or they're not going to go. So this means that EMR behaves like a particle and that each photon either has the potential to collide with a single electron and release the electron, or the photon doesn't have enough energy to release that electron. So one photon, this is really important, one photon only has the potential to release one electron from the metal surface. If no current was detected, so if this meter was not picking up any readings, then that means that the photons have a frequency less than the threshold frequency. So threshold frequency is the minimum frequency required to emit any electrons from the metal surface. Okay, the minimum amount of frequency required to emit any electrons from the metal surface. If the light is below that threshold, there won't be any electrons emitted and there won't be current detected. Okay? The intensity or the brightness of the light source is a measure of the number of photons emitted by that light source. So if a very intense light source means that many photons are being emitted. If the photons from the light source have a frequency equal to or greater than the threshold frequency, frequency equal to or greater than the threshold frequency, the current will increase as the intensity of the light source increases. The current. Okay? If photons from the light source have a frequency equal to or greater than the threshold frequency, kinetic energy, this is where we're going, kinetic energy of the emitted electrons will increase as the frequency increases. And the frequency will increase if the kinetic energy is increased. So what we're looking at is the kinetic energy in is going to be equal to the kinetic energy out. This is based on the conservation of energy, otherwise known as principle number 5. Okay, and so what we're looking at is the incident light, the energy of one photon that's hitting that plate, releasing the electrons, is equal to the kinetic energy, one emitted electron, and work is the work function. So work function is the minimum amount of energy. Oh, one other important thing here, because we're, wrong way. Because we're looking here at incident light and we're looking at work, we can have answers in joules or electron volts. And we'll see where we work later on with just kinetic energy that changes a bit. But for right now, if we're looking for our incident light, we can work in joules or electron volts. So work function is the minimum amount of energy required to release that electron from that metal surface. So we have a minimum amount of frequency required, we have a minimum amount of energy required, and that in order to get those electrons to go off of that plate and through the multimeter. So work function and threshold frequency have a relationship. W is equal to HF naught, F naught being the new language here. F naught being threshold frequency. Okay. Kinetic energy of the emitted electrons can be measured by applying a voltage difference to the photoelectric apparatus. So we could hook up a voltmeter and we could measure the amount of volts, which would then be looking at decelerating the electrons. So if we're decelerating it and we're bringing it to a stop, that voltage is called the stopping voltage, and it's represented by the following equation. So now we're starting to draw on work we talked about in Physics 20. This we talked about in the last unit. So E, kinetic energy, the maximum kinetic energy required is equal to the charge times the stopping voltage. And this is really critical. EK max, the maximum kinetic energy required, can only be in joules. Okay, so we know again from our data sheet that 1 electron volt here right underneath Coulomb's law, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So we can convert back and forth, but EK max's answer will be in joules. Threshold frequency of a particular metal. Threshold frequency, F naught, is equal to 1.14 times 10 to the 15th hertz. What is the work function of the metal? So again, I arbitrarily chose 6.63. You can use 4.14 times 10 to the negative 15. And this answer here is, of course, not the one I have. .56 times 10 to the negative 19 joules. If you had chosen the other one, 4.14 times 10 to the negative 15 times 1.14 times 10 to the 15, you would end up with 4.72 electron volts. So either answer is good. I just arbitrarily choose 6.63 because it's first of the two. Electrons are ejected from a photoelectric surface with a maximum kinetic energy of 1.92 times 10 to the negative 19 joules. If the incident light has a wavelength of 4.1 times 10 to the 2 nanometers, what is the threshold frequency of the photoelectric surface? Okay? So our information here, EK max is 1.92 times 10 to the negative 19 joules. Wavelength is equal to 4.1 times 10 to the 2 nanometers. When we look at putting in we get 4.1 times 10 to the negative 7 meters. And we're looking for the threshold frequency. Okay, so here the threshold frequency of the photoelectric surface. We're going to look at conservation of energy. Also, here, our answer is in joules. We're going to keep working in joules. Okay. All right. Energy in has to equal energy out. That means that the incident energy is equal to work plus EK max. And I know the formula says EK max plus work. They're interchangeable. 1 plus 2 equals 3. 2 plus 1 equals 3. We're good to go. HC over lambda is equal to HFO plus EK max. Okay, because we don't have E incident and we don't have work, but we can figure out that information based on the formulas that are used for each one of those. So we have 6.63 times 10 to the negative 34. We're now committed to using this one specifically because we are working in joules. 3 times 10 to the 8. 4.1 times 10 to the negative 7 is equal to 1.9. Nope. That's what we're looking for. Okay, 1.92 times 10 to the negative 19 joules. Right now, it's just easier to isolate the HFO versus trying to go directly into isolating the FO. And so when we do this math, we get now I'm going to move the H over. FO is then going to be equal to okay. You're going to make sure you carry your decimals all the way through. All right. The work function of silver is 4.72 electrons, electromagnetic radiation with wavelength of 2.5 times 10 to the negative 7 meters, strikes a piece of pure silver. Determine the speed of the electrons emitted from the piece of silver. This is where we're starting to see the crossover between physics and chemistry. Our work equals 4.72 electron volts. Our wavelength is 2.50 times 10 to the negative 7 meters, and it's looking for the velocity of the electrons. Okay? So what we notice here is this is in electron volts, so we need to pay attention to that. Energy in equals energy out. The incident energy is equal to work plus the maximum kinetic energy. Okay, so The reason that we're isolating for maximum kinetic energy is because we need velocity, and we know that this E is equal to 1/2 mv squared. Okay, or EK is equal to 1/2 mv squared. Because we're working in electron volts, we are going to keep doing that. This is, I share it in here, this is broken down into HC over lambda. And our work is 4.72 electron volts. EK max is then equal to 0.248 electron volts. However, EK max can only be in joules. So we're going to multiply by 1.6 times 10 to the negative 19 joules for every electron volt equals 3.97 times 10 to the negative 20 joules. You're going to keep all of your decimals because we're not done yet. Looking for the speed. (9.11 times 10 to the negative 31). This is the mass of an electron. Okay? We're going to take the square root of all of that to get our velocity. Okay, so the speed of the electron emitted from that piece of silver when a photon hits it is 2.95 times 10 to the 5 meters per second. So moving relatively quickly. Okay, a light source with a frequency of 6.65 times 10 to the 14 hertz is shone on a piece of copper. This is another key word, shone on. If you're shining light on something that's metal, remember it has to be a photoelectric surface, which would be metal. Shone on a piece of copper is the photoelectric effect. You know that you're going to be working with E equals HC over lambda, or E incident is equal to work plus EK max. You're going to be working in this realm of formulas. In order to bring the emitted electrons to a stop, a voltage of 0.48 volts is required. What is the speed of the emitted electrons? So the information that we have stopping voltage is 0.48 volts. It's going to be really important that you start putting units in if you haven't been in the habit of doing that, because this V here that we have, if we're not paying attention, if I look at the size of this F and the size of that V, then I'm going to think that maybe it's velocity. So make sure you're putting your volts in. And your velocity of your electrons equals is what we're looking for. Okay, in order to find velocity, we need EK max is equal to 1/2 mv squared. In order to get this, we know that EK max is equal to the charge of an electron times the stopping voltage. So EK max is equal to 1.6 times 10 to the negative 19 coulombs, which is the elementary charge, times 0.48 electron volts. Here we're looking at not electron volts, sorry. volts. And this is coulombs. We get 7.68 times 10 to the negative 20 joules, because joules is what EK max is always written in. And then we put it back into our original formula that gives us velocity. So we have 7.68 times 10 to the negative 20 times by 2 divided by the mass, 9.11 times 10 to the negative 31 for our mass of an electron. We take the square root of that to get velocity. So EK equals 1/2 mv squared was our original formula. The velocity of the electron is 4.11 times 10 to the 5 meters per second. Okay? When we look here, we see a whole host of questions. Yes, it looks like a lot. It only took me 45 minutes to get them done, so you should be okay. When you do question number 18, it requires information from question number 17, and you can still solve it. This is a numerical response. You're going to see approximately 16 of these on the diploma, so we're going to start paying attention to them. Classical wave theory and quantum physics make different predictions about the effect of incident electromagnetic radiation on photoelectric surface. So there's 4 predictions that are made. Low intensity electromagnetic radiation on a photoelectric surface for long periods of time will cause photoemissions. High intensity electromagnetic radiation will not cause photoemissions unless its frequency is greater than the photoelectric surface threshold frequency. The energy of the emitted photoelectrons will increase if the intensity of the incident electromagnetic radiation is increased, and the energy of the emitted photoelectrons is independent of the intensity of the incident of electromagnetic radiation. So the question is asking us, match each of the predictions above with the appropriate theory of physics as labeled below. There's more than one correct answer. So here we go. When we're looking at this classical wave theory, if we look at the first one, low intensity on photoelectric surface for long periods of time. This is not quantum physics, because the definition that we just looked at was that it's either going to hit it and the electrons are going to bounce off, or the photons are going to hit the surface at not the right frequency and the electrons won't be released. So one is classical wave theory. 2, high intensity electromagnetic radiation will not cause photoemissions unless its frequency is greater than the threshold frequency. That's 2. The energy of the emitted photoelectrons will increase if the intensity of the incident electromagnetic radiation is increased. This is going to be the classical wave theory here. And 4, the energy of the emitted photoelectrons is independent of the intensity of the incident electromagnetic radiation. This one we find here. Okay, this all goes back to the very first set of notes here. All right. I will let you get to these questions here. Oops. These questions here.